Scott, and I've been building products at Tandem, Microsoft, Amazon, and now having a great time at Salesforce. Started my career doing that in distributed systems and databases in 1978, so I realize that's 39 years now. I've been building distributed systems, worked on one of the first two-phase commits at Tandem, and have a lot of fun. And recreationally, I just write down random crazy stuff I think of, and it's a lot of fun. And so the talk I want to give you is called Standing on the Distributed Shoulders of Giants, and part of my branding is silly names for talks. And so the paper that goes with this is in the communications of the ACM. ACM is Association for Computing Machinery, and that is the trade organization for nerds. Okay, if you're in computer science, that's the thing you do. And they've asked me to write a column, and so I get to write up to 6 times a year and publish, and this is just the first one I got done last year. And the point behind this paper is if you look at the insights of our brilliant physicists, wow, there's a lot of interesting parallels to what we do in distributed systems. And those physicists were pretty dang smart, even though there weren't computers back then. What the hey, right? So we're going to look at 5 different great physicists. Newton, Einstein, Hubble, Heisenberg, and Schrödinger all had thoughts which make me realize they understood distributed systems way before there were computers. Go figure. So let's look first at Newton. Newton was arguably our most brilliant physicist. He did classical mechanics, laws of motion, universal gravitation. He built a refracting telescope, developed a theory of color. He was a bad dude. This was 350 years ago or so. Very much like single computers, because one of the things that happened with him was he assumed time marched forward universally everywhere, all the time. And that's how it was back when I started working in computer science, right? Transactions give a clear notion of time in databases and so forth, but there's only one time. This transaction follows that transaction. Back when I studied computer science, seriously, literally, Nixon was president. We did not talk about the relationship between the clocks of 2 different computers because computers barely talked to each other, usually with a mag tape, sometimes with something coming across the wide area network, but that was just a faster or slower mag tape. Okay, we didn't think about it that way. Now, Einstein, what a cool dude, right? In 1905 alone, he published 4 world-changing papers in one stinking year. Photoelectric effect, Brownian motion, special relativity, mass energy equivalence. Wow! But special relativity was based on 2 principles. All the laws of physics, including time, appear the same to all the observers. Now that meant if the speed of light is unchanging, time must change. And there are really interesting consequences to special relativity. Guess what? The sun might have blown up 5 years ago and the next 5 minutes ago, and the next 3 minutes are going to be wonderful. And then it won't be so good. Stuff that happens far away takes a long time to learn about. And so that's this really, it messes with your brain. But it's just, you can't know. In computing, you can't know what's happening over there. You can know what's happening here. You cannot know what's happening over there. You got to send a message and say, dude, what's happening over there? And then you got to wait for the answer to come back. Latency is a major design point in such a system. Unlike in physics, in distributed computing, we can't even know how long it's going to take because it's not just speed of light that slows it down. With Einstein, it's hard to get in the last word. You have no idea if a message has gotten there in bounded time. Not in bounded time. Eventually, you probably know, right? The longer you wait, the more likely you'll know that it got there. But you have no idea in bounded time. So if you look at the first one on the left, it is not guaranteed that little last one ever gets there. It's not guaranteed those last 2 going in the same direction get there. As a matter of fact, the sender of the last message cannot know it arrived, ever. The only way to know is to have another message, and then it's not the last message. And so this has got to be in your soul. You cannot know what you don't know in a distributed system. Now, it takes a long time to agree. Messages and servers live in their own different time space. So look at this. Server A's got his time reality, His clock's marching forward, he's doing his thing, sends a message off to server C, and he sends a message off to server B. Well, guess what? Because of the timings in more than one server, you can't even know the orderings in which things can happen. A can send to C, C can send to B, and that gets there before the message that A sent earlier to B. Everything. You need to think about the network as a bunch of Machiavellian gnomes that will deliver that message at the worst possible time, because things get buffered, stuff pops back up, and it's really crazy to figure out unless you have causal knowledge that this caused this caused this. You cannot do distributed consensus in bounded time. You can do it. It usually works within this window of time, but you can't know it because messages get lost, they get retried, they will probably get delivered. Every message you send gets there 0 or more times guaranteed. Now, there's usually a lovely probability spike up around 1, but 0 or more guaranteed. Two-phase commit, Paxos and Raft, cannot guarantee agreement in bounded time. They do have a very nice probability distribution. They usually get it done quickly, but when things go wrong, it can take a long old time. And then they're very likely to reach agreement soon, but no guarantee. Each has its own world. Each is in its own relative thing. How do you figure it out? So Einstein capping it off. There's this wonderful theory, was a conjecture, now it's been proven, it's a theory, called the CAP theorem. Consistency, availability, and partition tolerance. You can have any two, pick whichever two. But I want to point out, consistency means classical transactional consistency. When Randy said wonderfully about the long-running workflows and undo and compensate, right? It's great. That's how it works. That's how it really works. It's also not classic transactional consistency. Okay? And so you kind of need to loosen up on this consistency thing and realize that insanity is a good part of life. Okay? It's okay. So now two-phase commit provides strongly consistent transactions. Its job is to give up on availability. Its job is to say, that ain't perfect. Nope, I'm not going there. And so it shuts down if it's not perfect. Two-phase commit is the anti-availability protocol. And I was quoted on that in 1988, okay, when I was working on it. Hubble was increasingly far out. Edwin Hubble discovered that the universe is expanding. The farther away an object is, the faster it's going away from us. This was really a mind mess. It was like, huh? Everything's getting farther away from everything else. In computing, there's been an amazing run. We've just had such a great time, I think we will continue to in many ways. We've seen an ever-increasing amount of computation, of bandwidth and memory, and I do believe this will continue on with some changes as we move forward. But you know what? Latency is not dropping that much. The time it takes to get a message from here to there, yeah, it's getting faster as the pipes get faster, but it's kind of hitting the limit where the speed of light is a big portion of the time to get from this server to that server, even in a database, even a data center, right? So the number of instruction opportunities lost while something is fetched is increasing. What do I mean by this? I'm going faster here. Think, 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 think. And my next server is faster. Think, 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 think. And the next one's faster. Think, 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 think. Now, meanwhile, that message talking to the next guy has taken the same amount of time. So I've gotten a heck of a lot more done over here while waiting for that answer over there. So it's putting increasing pressure on our algorithms and systems to understand how to make all this stuff come together. Computing is like Hubble's universe. Everything is getting farther away from everything else. In 1992, I was working on a cache-coherent, non-uniform memory architecture multiprocessor, and I was realizing, dang, that other server is like way the heck over there, and it's hard. Hubble didn't share very well. As stuff recedes, sharing read-only data isn't the biggest problem we have. It's actually not that hard to cache stuff. And you can talk about statistics of a cache hit. And that's one of the glorious things about immutability. That's why I wrote the paper that Nihan so kindly mentioned called Immutability Changes Everything, right? And the more you have stuff that doesn't change, the more it's immutable, the more you can have it close to what you need when you need it. With enough cache, you can have it. So that's not the big problem. But if I'm updating things, if I'm changing things, then I have to play what I call the tug of war. I have to pull that permission for that record back to do it. I have to pull the cache line back for write access in a multiprocessor. And I have to stall while I'm getting the latest one. And because I have more opportunities to think while I'm waiting to get the permission to write, this is more and more painful as time goes on, and it behooves all of us to build our systems to be less dependent upon that. Shared memory works great as long as you don't share memory. Okay, does that make sense to everybody? We need to do something about this. Folks in our industry need to change it. We have two choices. Either get around that pesky speed of light thing, or start thinking more about immutability, asynchrony, and concurrency. Heisenberg was not sure. He defined the uncertainty principle. The more you know about the location of a particle, the less you can know about its motion. It is theoretically impossible to know both. Basically, you cannot know everything about anything. In a distributed systems, you have a gaggle of servers. There's just a lot of them. It's hard to even count how many you have in a big distributed system nowadays. They're all in various states of health, death, or garbage collection. And garbage collection is even more painful than death, because it's like, what do you mean you're answering me now? Whoa, shoot, I wasn't counting on you. It's just really complicated when something goes slow. Other times it just takes, most of the time you get an answer which says, whoa, no, yes, no, I got the answer. Sometimes you're just waiting and waiting. And it's like going shopping with my wife. It's like waiting, right? And anytime you talk to a single server, you don't know it will be delayed. So in many distributed systems, the response time is very, very important. Human beings really get annoyed when it takes a long time. So if the response time is important, you have to launch multiple requests and then take any of the answers you want. You don't care where the work happens, you just care when it happens. So if you are a distributed systems person, you need to read this paper. It's amazing. And so it was written by Jeff Dean and Luis Andre Barroso in Google. It was a couple years ago in the ACM Association, the communications of the ACM, and it's called The Tale at Scale. It's about managing latency at Google. Now here they're talking about read-only requests, and specifically a portion of a search. Imagine a Google search, you have to go and get answers. You need to get answers from 100 different servers to figure out where it might be. And so it's a read-only request. Idempotent, no big deal if it's issued twice. So shared resources, there's a natural variability because of shared resources, garbage collection, maintenance, all of that kind of stuff. What they do is wait. They launch a request. They know when the 95th percentile response is. How long does it take? So 19 out of 20 of the requests are done before that. And if I've launched 100 different requests, and these 5 are waiting too long, I'm going to relaunch them to other servers. Now that answer is fine. Now I can give you the answer that was waiting for all 100, and I can do it. The observation I want to share with you is we can do this for writes too. Specifically, I was working on how the heck can we do a logging system for an online database system that humans, many thousands of humans, are waiting for the answer for the log. Okay? If you write that to a classic, strongly consistent thing on top of normal servers, if any one of them does a garbage collection, you stall. And that's very annoying to have thousands of customers stall. So some tricks up our sleeve. Number one is 2 out of 3 ain't bad. You launch the writes to 3 requests, you wait for 2, and then once you got 2, you say, I'm happy, I got 2 of them. And that if 2 is enough that you can then later on make 3 and have a low, low, low probability of losing the data. The last one is love the one you're with. You write to 3. If you get no response from 1 or more, you find others. So eventually I can find it. But the goal is to bound the SLA by finding some place to write 2 and then rapidly cleaning it up to 3 replicas. 3 replicas in the data center. It's pretty well understood that the statistics of server failure means you're going to lose the data center to a flood or a fire or something much more likely than losing 3 of them. But I might have reordered things. I didn't get it to the same 3, so how do I deal with that? Because remember, I got 2 here, maybe I get 2 there. Now, if I'm just reading in the order they arrived at the servers, that might be tangled up. That says, as I write them, I have to count. Here, let's do the first one. Let's do the second one. Let's do the third one. And if they get in the wrong order at the single individual place, it doesn't matter as long as I have an identifier on it so I can recreate the intended order at the beginning. So what's interesting is that the inability to know where it lands over there means that I need to define the order at the place it's emanating and needs the order. The intended order has to be assigned by the database. Assigning it at the database or client allows durable writes to any replica while preserving order. The tolerance of where you write, I don't care which servers it lands on as long as there's 2 of them, allows you to have much better control over when you write. Because it's highly unlikely that that 2 servers are going to stall at the same time. So I can have a much better control on the timing. And so, but that is a very interesting aspect. So the point I want to make is, in a distributed system, you can know where you write, or you can know when you write, but you can't know both. Does that make sense to everybody? Schrödinger's cat. So Erwin Schrödinger was this leading physicist, and he made really seminal contributions to quantum theory and more. But he's remembered for this thought experiment because he was really annoyed at this whole idea of superposition of state, where I don't know if this atom has decomposed or not decomposed. That just seems so wrong. So what he said was, that theory, the math, the observation shows everything stays in multiple states, and the act of looking at it causes it to collapse into one of those states. Now, Schrödinger thought this was really, really goofy. And so he said, this is so goofy, what if I look for that happening, and I look for the Geiger counter saying, yes, 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 this atom has decomposed, and then it will hit a vial of poison, and it'll hit a cat and the poison and the Geiger counter and the atom are all in a box. Is the cat alive or dead? Well, guess what? Most physicists today actually believe that the cat is both alive and dead until you look. It's kind of counterintuitive, but that micro turning to macro has interesting effects. So I want to posit there is a thing called Schrödinger's put. If I go to write something to a distributed store, and then I crash, is it there? Maybe. How do I know if it's there? Look. And if I look, and then I make it be durably there, you get into this world. Well, did it land on all 3 servers? Did it land on 1 server? Was the 1 server in which I looked down at the time, then you kind of come back up and you make it not count. There's a whole bunch of algorithms we have to recover from stuff which clean things up in that fashion. And so the client issues a put. When the client fails during the put, we don't know where it's written. So while not yet observed, a put does not really exist. It's likely to exist. Only after being seen with a get and pushed back will it definitely exist. So conclusion, wow, those guys were smart. How the heck did they know all that stuff, right? Their discoveries seem so counterintuitive, and those natural things are only true, but at the limit, they're not. They're at the true in the grand scheme, but at the limit, they're not, and we deal with that in our systems today. Isaac Newton defined how stuff worked if you assume time is universal and march forward, one now. By the way, that's the way I grew up with databases. That's how, and I am like on record for being the biggest transaction guy you know, having done all transaction junk back when I had hair, I was doing transaction stuff that long ago. And so, but I still believe they're a powerful tool, but they're a powerful tool in the small, not necessarily in the large. Albert Einstein realized that everyone has its own independent clock allowing constant speed of light. Your now is not my now. That is very deep in distributed systems. Hubble, the universe is expanding. Everything is getting farther away from everything else. Again, a surprising result that affects what we do today. And Heisenberg, as you get smaller, you have to pick what you need to be accurate and allow the other stuff to be inaccurate. All of these principles permeate our distributed systems design. Kafka is an example of a great distributed system. Fascinating project. And these are things that my friends at Confluent think about as they go through life. So thanks for your time.